All right, homework 17 is continuing where homework 16 left off, where we're doing that hypothesis testing. Last time we did the z-test, and now we're going to do the t-test and the chi-squared and all of those. Keep in mind, for those of you who may have not gotten everything read yet, we have one-tailed test where you're checking to the left or to the right. We have a two-tailed test where it's a not equal and you're testing both of the two little ends. So on number 1 here on homework 17, we're going to do the t-test this time. It says, it seems these days that college graduates are employed full-time, work more than 40-hour weeks. Data are available that can help us decide if this is true. A survey was recently sent to a group of adults selected at random. There were 16 respondents who were college graduates employed full-time. The mean number of hours worked per week by these 16 respondents was 44 hours, with a standard deviation of 9 hours. Assume that the population of hours worked per week by a college graduate employed full-time is normally distributed with a mean of u. We can conclude that the mean is greater, or can we conclude that the mean is greater than 40 hours? Use a 0.1 level of significance. This is going to be a one-tailed test. The reason we use a t-test instead of the z-test is because we don't know the standard deviation for the population. We know the standard deviation for a sample standard deviation. So it tells us to perform a one-tailed test because we are going to try to see, can we conclude that the mean is greater than 40 hours? Is the mean greater than 40? Remember, we have our two hypotheses, the null hypothesis and the alternate one. The null always includes the equal sign. Since this doesn't have an equal sign in it, it's our alternate one. Our mean is greater than 40, which means the null hypothesis would be, is the mean less than or equal to 40, right? If it's not greater than, it has to be less than or equal to 40. So, they're going to have you choose what kind of statistic, just like last time, way back when we had class. We used the z-test if the standard deviation was known for the population. We use the t-test if we know it for the sample. And so here we're going to just pick that we're doing the t-test. So, the formula, it's going to look pretty much like the formula for the z-test. Looks like this. T is equal to the sample mean minus the given mean over the sample standard deviation divided by the square root of n. So we got to find those things from our problem, but I zoomed up so you'll have to read on your paper. So, first thing we want to know, or for our formula, is what is the mean of the sample? What is x bar? So if you read through there, for the sample, what is the mean that they tell you you have? .44, exactly. That's what it is. Then we're going to do the mean from the population, which is what we're actually going to be estimating. And that'll be this number here that we're trying to compare it to. Is the mean really 40 hours? Then the S is your sample standard deviation. The sample standard deviation is how many hours? 9. And then N. N, how many people did we survey? 16. All right, so we're going to plug our numbers into our formula. We are going to have 44 minus 40 over 9 divided by the square root of 16. And you can either use your regular calculator to do that or the Alex calculator, whichever one you want to use. To come up with your number, it says we're going to round to at least 3 decimal places.
1.778.
Yep. 1.778 is our test value. So when we're thinking about this, we're going to think about our curve. Our critical value is 1.778. We are testing, is it greater in that section, right? U is greater. We are going to do the p-value. There's two different tests. There's a p-value test and the critical value test. For the p-value test, we are going to then use that p of t thing we worked on before on the Alex calculator. P of t. On Alex, P of t is greater than, right? If this is a greater than, which it is, then we don't have to do the 1 minus. If it's a less than, then we have to do the 1 minus because we're doing the opposite way. P of t is greater than 1.778. And on these ones, when you do the t-test, you had to do the degrees of freedom. On the degree of freedom, it's always 1 less than n. So the degree of freedom is going to be n minus 1. 16 minus 1 means I have 15 degrees of freedom. These ones, it's best to do the Alex calculator. So now you're going to use your Alex calculator. I think you can get to the calculator, yeah. And you're just going to put that in. .0 or 0.048, yep, is my p-value. The p-value is really a percentage. We were checking, is it at this level of percent or not, right? If the p-value is less than that number, we're going to reject the null. If the p-value is greater than that number, we're going to accept the null. So my p-value, 0.048, comparing it to 0.1, is that less than or greater than? It's less than. If this is a less than, means it's not true, we're going to reject the null hypothesis. That means we're going to say this is not true, this one is true, right? I'm just going to write that in there. Okay? So if it's a less than, you reject whatever the null is. If it's a greater, you accept whatever the null is. So it says then for the question, can we conclude at the 0.1 level of significance that the mean number of hours worked by college graduates is greater than 40? Yes, we're saying it is greater than 40. That was the true statement, right? So yes. Is it greater than 40? Yes, we're accepting that second statement. That was the true one. On your calculator, now because it has degrees of freedom, sometimes your numbers are slightly off, but they should be fairly close to what you got doing the Alex calculation. But on your Alex calculator, we are going to go to the stat function. So hit the stat. And then remember we went cursored over to the tests. And this time we're going to do the t-test. Last time we did the z-test. So we're going to do number 2, which is the t-test. And we have the statistics to put in there. So if data is highlighted, cursor over to stats. Okay? So the U0 is the same thing as the U here. What are we comparing? That's going to be our 40. X bar, 44, what we had there. Sample standard deviation is our 9, that's our S. Number in our sample is 16. Unfortunately, it doesn't give you a spot to do the degrees of freedom, and that's why we always end up a little bit off. We are doing greater than 40, so you want to make sure that the greater than 40 is highlighted. And I like to do the draw one instead of the calculate one, even though the calculate gives you the numbers. But the draw gives you the picture too. Ooh. My picture went clear off my screen. Where did I go? Oh, it's drawing. It's just slow. It's still drawing. So, you'll see in the little picture that they have their little curve and their shading greater than, because that's where we were testing. You see our test value is 1.7778. They rounded, they're going to carry a few more places than we did. They said their p-value 0.479. We rounded it up to 4.8. So it's pretty close, right? So if you want to check your answers, you can check it using that stat function and check the tests. You still need to know how to interpret it, but you can check your values. Alrighty. So, number 2 there. A citrus rental is a popular car rental agency that has a history of having too few cars available, so that its available cars are overdriven. The mean monthly mileage over the years for the citrus car has been about 1,550 miles. Recently, though, Citrus purchased thousands of new cars, and the company claims the average mileage of its cars is now less than in the past. I was just making sure I hit record. To test this, a random sample of 10 recent mileages of Citrus cars was taken. The mean of these 10 mileages was 1,467 miles per month. Standard deviation is 245 miles per month. Assume that the population of a recent monthly mileages of Citrus cars is normally distributed. At the 0.05 level of significance, can it be concluded that the mean recent monthly mileages of Citrus cars is less than 1,550 miles per month? So my statement is saying, is the mean less than 1,550? Since that doesn't have the equal in it, that's my alternate hypothesis. My mean is less than 1,550, which means my null hypothesis is going to be my opposite of that. What would my null hypothesis be? The mean is greater than or equal to my 1,550. Exactly. Again, we know because we're doing the t-test that it is the t-test, but we do that because we know the sample standard deviation, not the population standard deviation. So if we know the sample standard deviation, we're going to do the t-test, because when you take the assessment, it's not going to come right out and say, use the t-test. So we need to find the value of the test statistic using our formula. X bar minus the mean over S divided by the square root of A. So, in this case, our X bar number is what number there? What is the mean of the sample?
1467.
Exactly, 1467. Then we have the mean that we're trying to compare it to, which is the 1,550. Our sample standard deviation is 245, and then N. How many people did we check? Or cars? We didn't check very many cars. How many cars did we sample? How many mileages did they test? 10. There's only 10 there, yep. And it's going to be 10. One other thing we're going to have later, or may have, is the degrees of freedom. If they do need the degrees of freedom, it's always n minus 1. So if we need to put that in somewhere, our degrees of freedom would be 9. All right, so we don't need that on the formula, but we might need that later. Plugging into our formula. 1467 minus 1550 over 245 divided by the square root of 10, and we're rounding to at least 3 decimal places. Okay, are you using the Alex calculator?
Yeah.
Okay, so we are going to do the 1467 minus the 1550. Then we're going to highlight that and do the divided by. On the bottom, we're going to do the 245 divided by square root of 10. So when I have more than one thing with adding and subtracting and we want the whole thing divided by something, then we're just going to highlight it. Okay? So we end up to 3 decimal places with what number? Negative 1.071. Okay? So on this one, we are testing less than. But we're not doing the p-value, we're doing the critical value. When you do the critical value, instead of doing the p of something, you're using that t sub something. Remember we had those 2 different ways of finding the values? So you're going to do t sub, and my test point is this number here. So you're going to use that number there, 0.05, and I think you have to have the degree of freedom. Yes, you do. The degree of freedom is 9. Now, to make this work outright, because I'm doing a less than, I have to do a negative value. So if it's a less than, a left-tailed test when you do your critical value, you want that to be negative instead of positive. And then you're going to punch that into the Alex calculator. Do you see where the t sub is? Right there, yep. You probably want to put a negative in front of that, or at least put a negative on your answer. I'm just going to write, since it's left-tailed, we got to make sure we put that negative. If it was right-tailed, we wouldn't need negative. All right, so when you put that into the Alex calculator, what did you come up with for a number? Yep. Negative 1.833 is what you get. So what they're saying is this line right here is at negative 1.833. You're trying to decide, is this number in that section or not in that section? Where would negative 1.071 be? Would it be over here or over here? Is it bigger or smaller than negative 1.833, in other words? It's bigger, right? Since this is negative? Negative 1.071 would be in this section over here. Okay? This section to the left is this, which is our H1 answer. This section over here, then is going to be our null answer that's greater than or equal to. So, we ended up being in this section with our null. That means this is the true statement, this is the not true statement. I'm going to word that. So, at this level of significance, can we say that the mileage is less than 1550? Can we say it was less than 1550? No, because that was the not true statement, right? We said the true statement was that it was greater than or equal to the 1550. So no, we can't say that. It's not true. Based on our statistics, it's not true. Okay? So, p-value, you check the percentages. You're comparing the percentages. Critical value, you're finding where this line is and then deciding, is my test value, which side of my line is the test value on? Greater than, less than, depending on what you're checking. Where's that? Don't worry, we got a whole bunch of hypothesis testing. Hopefully by the time we get to the last kind, you'll go, oh yeah, now it's kind of making sense. All right, a coin-operated drink machine was designed to discharge a mean of 7 ounces of coffee per cup. In a test of the machine, the discharge amount in 13 randomly chosen cups of coffee from the machine were recorded. The sample mean and the sample standard deviation were 7.01 ounces and 0.21 ounces respectively. If we assume that the discharge amounts are normally distributed, is there enough evidence at the 0.1 level of significance to conclude that the true mean discharge differs from 7 ounces? So this one's a little bit different because it says it differs. If it differs from something, it means that the mean is not equal to my 7 ounces, right? Differs, does not equal. I'm going to have a two-tailed test instead of a one-tailed test because I'm looking for the part in the middle or on the two ends, depending on what the question asks. So this does not include the equal. That's my alternative, I should say, hypothesis. Which means my null hypothesis is that the mean actually does equal 7. Right? The null always has the equal. So if I have one that says differs, my null will be it does equal. My alternative one does not equal. Again, it asks for what type of test you're using. Because you know the sample standard deviation, we know we're using the t-test. So we want x bar minus the mean over s and the square root of n. So the sample mean was 7.01. The mean we're comparing it to is
0.21?
nope.
7?
7. Yep. The sample standard deviation is 0.21, and n is 13, which means my degree of freedom is going to be 12. 13 minus 1 is 12, right? It's always n minus 1. I just do that right away while I'm doing the rest of my numbers because I know I'll probably need it later. So, again, plugging those into the formula. 7.01 minus 7 over 0.21 divided by the square root of 13. That's what we want to punch in. .172. Okay. So when we do this test, we have what's called a two-tailed test. I am going to do my test value, and so I'm doing the p-value, so that tells me I'm going to do the p of t. I am going to do p of t is greater than the 0.172 with a degree of freedom of 12. That's going to tell me the number for this section, which is also going to match the number for this section because there should be the same size if I could draw straight. But first we'll find our number. So, that's supposed to be 0.172, right? So, on the Alex calculator, you're going to do P of t is greater than 0.172 with a degree of freedom of 12. 0.433, you said? 0.433, which means this one is also 0.433. So when you write down what is the p-value, you're going to add these two things together, or you could just multiply by 2 because it's the same number, because I got the same number on both ends, right? So if I multiply that by 2, I have 0.866. And then we're going to compare that p-value to the level of significance. So, 0.866, is that greater than or less than 0.1, which is the level of significance that we're testing? It is greater. Now from the first problem, do you remember, if it was a greater, do we accept the null or do we reject the null? Check your problem number 1 out. I said there in problem number 1, if the p-value is less than my level of significance, we are going to reject the null. If my p-value is greater than the level of significance, we're going to accept the null. It's going to be true for all your hypothesis testing, so write it down somewhere. If it's greater, or if it's less, then you reject it. Reject the null. If it's greater, accept the null. So we got that it was greater. That means we're going to accept the null statement. The null statement is going to be true. That means the other statement is our not true one, right? So the question says at the 0.1 level of significance, can we conclude that the true mean discharge differs from 7 ounces? Can we say that it differs from 7 ounces? Which one was our true statement? The true statement was that it equals 7 ounces, right? So we can't say that it differs because it's equal to 7 ounces. No, we can't say that it differs. That one was not true, the differ one, right? That is not true. I know these are tricky. All right. Again, I forgot to remind you that if we wanted to check our test statistics, we could check them on our calculator using our stat function, right? So just for fun, let's just check this one. So I'm going to hit stat, cursor over to tests, and we're doing the t-test number 2. We want to use the stats, not the data, so the mean value is the 7 here. So when they ask for first, our x bar value, 7.01. Sample, the 0.21. N was 13. This time we were doing the does not equal the mean, so we want the first one highlighted instead of the greater than we did before. So hit enter on the does not equal, and then go to the draw. And slowly it should draw for you. It's not the speediest of graphing your picture. Oh, we got quite a bit shaded in blue. See, I had too big a gap in the middle. Tells me my t-test value, 0.1717, pretty close to what we got, right? My p-value, 0.8665. So we would have just been a little bit off because we would have rounded up to 7 if we were using our calculator. But I think Alex does let you get a little bit off on the rounding because of some people using technology instead of using the formula. So gives you pretty close to those numbers, right? Now, if you do the critical value, you don't see that, but you do see the p-value if you're doing the p-test, or the p-value there. All right. That is the t-test.